Good afternoon, everyone. Thank you very much. So as you heard, my name is Christopher Dobrian from the University of California at Irvine, and Omar Costa Hamido from here at University of Coimbra. So before we start, I'm going to give an intro to the intro, which is to say that this is, in our minds, a very introductory paper and a very introductory talk, sort of introducing our initial thoughts into this question of what are the correlations between music and quantum computing. And so as such, we're not presenting profound, deep findings after years of research. We're more projecting what are some possibilities that we think are potentially interesting, and we hope that that will engender conversation with you over coffee and dinner and so on. So I'll be talking briefly about some of the musical concepts that we've started with. Omar will talk about some of the technical implementation, and then we'll briefly talk about what we see as possible next steps. So our main idea is to explore correlations between quantum theory and music theory, and specifically between principles of quantum computing and musical harmony. And we're particularly interested in this as a methodology for composers. I'm primarily a composer of both instrumental and computer music, and in my music I'm very interested in trying to devise novel sonorities and novel harmonic grammars. And therefore, when I'm doing computer music, I'm very often involved with algorithmic composition or algorithmic improvisation using some harmonic system that I've devised to try to make music that is at the same time somewhat novel in its sound and also sensible tonally to the listener. So Omar asked me, what does harmony for composers mean? Because at my university I teach a seminar called Harmony for Composers, because I find that young composers often have a very unsophisticated view of harmony based on their undergraduate training in music theory, which at least in the United States is quite limited. And so there's a whole world of harmonic exploration post-Wagner that they have not really delved into deeply. And so I come at it from what I call a polytheoretic and a pan-stylistic, polytheoretic and pan-stylistic approach to harmony and composing. So how is harmony for composers different from any other sort of harmony, Omar asked me. And my answer is that harmony for theorists tends to be a retrospective view of music. One looks at a score that is already fixed, one sees that one chord progresses to another, and one then analyzes that chord progression based on an out-of-time view of the entire piece. One can see into the future, in effect, and one can see into the past. Harmony for composers, and particularly harmony for improvisers, is very different because you're in the musical moment. You're playing a chord perhaps on your instrument, and yet at the same time you're trying to decide where to go next. And so there might be a very obvious place to go next, but there might be other less obvious places to go, and that's really a composer and improviser's job, is to make that kind of decision, where to go next. But in that moment, just as I believe it was Edmund Husserl who pointed out that we're only hearing the present. We're not really hearing the past. We're remembering the past, and we're not really hearing the future. We're having expectations of the future. So we have retention and we have protension, but in the moment we only have the present, right? And we don't know of anything else. So it's a real-time creative activity, the practice of harmony for an improviser. And I would say for a listener, it's also a very real-time experience. You have heard the past, but you're not hearing the past now, and you don't know what's coming next. And in your mind, as an objective listener, almost anything could happen next. Although you might, of course, have expectations of what will be most likely to happen. So it's a real-time experiential reality for the listener. So although I don't think listeners generally listen with Roman numeral notation as they're listening, saying what chord they're on and where they're likely to go based on the harmonic function, but at every moment, the future is uncertain. Some chords are more ambiguous than others, obviously, and I call that the Schrodinger's chord. In the moment that we hear the chord, we don't know where it's going. It could be anything. Just in the metaphorical thought experiment of Schrodinger's cat, we don't know whether the cat is alive or dead until we open the box. So that moment when the chord is resolved, or in the case of quantum computing, when the qubit is measured, that's the moment when we actually realize whether it's a 0 or a 1. So this seemed like an interesting and kind of intriguing metaphorical relationship between the two fields that intrigued me, and that's when I approached Omar and said, let's talk about this. Is there anything in this at all? And so we decided to choose kind of the most obvious example of ambiguity of harmonic function, which is the diminished seventh chord, because obviously it divides the circle of fifths into 4 equal parts. Therefore, it has 4 equally likely roots and can resolve to either a major or minor chord. So if it has 4 possible points of resolution, and each of those points of resolution can be major or minor, that gives us 8 possibilities. And the thing, of course, that makes this possible is the equal tempered scale, which means that that an A sharp is the same as a B flat, that a C sharp is the same as a D flat, and so on in equal temperament. So that's what makes it possible for the circle of fifths even to be a circle of fifths, right? The classic resolution, no, I don't know, yeah. The classic resolution of a diminished seventh chord, if you see this first 2 measures here, when we hear that chord, we might or might not have an expectation of where it's going next, but perhaps the most obvious expectation, a C major chord followed by a C sharp diminished seventh chord, would be that we would go to a D minor triad. Oops, that was not good. Sorry about that. Thank you. I'll be careful not to touch anything. But as you all probably know, by inharmonically respelling that diminished seventh chord, we could resolve to any of the other 3 possible leading tone chords. So the second chord there is interpreting the E as the root of the chord, and therefore the D flat is the 7th of the chord, and we resolve to an F major chord. In the third example, the G is the root of the chord, and therefore the E is actually respelled as F flat, and takes us to an A flat major chord. And in the fourth example, what are we doing there? We're going to an A sharp diminished seventh chord, which then resolves to a B minor chord. So I've sort of quasi-arbitrarily chosen whether to resolve to a major or a minor chord in this example, but you can imagine there are 4 other possibilities there, which would be the opposite chord quality of resolution. So we have those 8 possibilities. And I should say that, if you've studied romantic or even just classical music, you'd know that really there are far, far more possibilities than just those 8. We could pretty much resolve to any chord that contains any of those 4 notes of resolution. So we could resolve to a B flat major chord, we could resolve to a G major chord, etc. And once you start talking about the possibility of resolving to a 4-note chord, then you're multiplying your possible chords of resolution greatly. So that's just to say that in this sense, the diminished seventh chord, particularly in jazz, can just about go anywhere. It's more of a sonority and a color than it is a function in a lot of music. And there again, I would say it's probably because not only does it have particular pulling tendencies, as explained in classical music theory, it also has no pulling tendencies because it's perfectly symmetrical. It has no interval to tell us that it should go one way or another. So it seemed to me like this was the perfect vagrant chord, as Arnold Schoenberg said, the chord that just will happily go anywhere. And so I decided to make this little thought experiment, which then became a little programming experiment, which was from any starting chord, which we'll just say is C major, choose one of the 3 possible diminished seventh chords, one of these 3 pitch class sets, then choose one of the 4 possible inversions, which will determine what note is in the bass or what pitch is in the bass, and then resolve to one of the 2 chord qualities, either major or minor, and then repeat that process. So that gives us 3 times 4 times 2, 24 possible results for every time we repeat that process. Now, needless to say, if we repeat that process over and over again, it's not terribly musically interesting, but just as a little demonstration of kind of what I think of as being the simplest possible demonstration of this, that's what I chose as the experiment for us to try and realize. But in the spirit of quantum computing, I said we should try to make all of the random decisions or all of the probabilistic decisions be done with a single bit. In other words, by resolving a qubit either to 1 or 0. So we decided to make all of our decisions using only single bits. rather than the standard process of using a random number generator. So for choosing between two options, you only need 1 bit, of course, and to choose between 4 options, you only need 2 bits. But for choosing between 3 options, it becomes a little bit clumsy in classical computing. I think that probably the accepted way to choose between 3 things with totally equal probability would be to use 2 bits to generate a random number 0 to 3. And then if it's one of those possibilities that you decide is the null possibility, you go back and do it again. Not terribly efficient, but not the worst thing in the world. But it seemed like maybe this was a place where the real superposition qualities of quantum computing might actually provide an answer to how to make decisions in a different sort of way. Whether it's a better way or not, entirely up to debate, but just as something for us to explore and to get us started with this idea of superposition in the case of a harmonically ambiguous chord. I'll turn it over to you.
Thank you, Chris. So for those of you who don't know, Chris is not only a great teacher and composer, he's also a great cook. So I thought that this idea, what he set up here is just a perfect recipe to now go ahead and try to make it or resolve it, work with it with quantum computing. So let me just loop back around on this presentation. Here's 2 different graphics to represent this idea of a loop, or however you prefer. Going forwards and looking deeper into itself. So to go back to the main idea, to explore correlations between quantum theory and music theory, specifically between principles of quantum computing and musical harmony, particularly as a new methodology for composers. I wanted to point that out again for a second. So Chris talked about 3 views of harmony, and I'm going to point out 3 views of quantum mechanics. We have quantum physics, we have quantum computing that I shortened as QC, and then we also have science fiction. I'm going to leave the last one aside. It's great, it's sometimes really creative and amusing, but I'm mostly focusing on the first 2, and I just wanted to point these 2 here side by side just to clarify something, which is that knowing a lot about quantum physics doesn't mean that you know all of that there is to know about quantum computing, and vice versa. Knowing a lot about quantum computing doesn't mean that you know all about quantum physics. I know more of quantum computing. I know very little about quantum physics, and maybe a great physicist would say that no one really knows everything about quantum physics, but that's another story. Okay, so what is this thing called QC? QC is a way to compute problems using quantum mechanics. So let's say that we have a problem and we want to find a solution using quantum mechanics and a quantum computer. We still need to use a classical computer. We need that to write our logical circuits, which is our set of instructions to compute the problem. We do that by using quantum circuits, and we write the quantum circuits using quantum gates. Then we send those set of instructions to our quantum computer, and there we make use of quantum mechanics and quantum mechanics phenomena like entanglement and superposition. But then when we want to retrieve our answer, we have to measure this quantum state. And this measurement thing, it collapses the states, and the information that we get is the information that we can read on the screen, which is our classical machine. So that's going to be now back into zeros and ones. So previously we talked about ambiguity of harmonic function. So here this quantum state is ambiguous, has this ambiguity in itself. And this is because a quantum state is a complex state. It can be in a superposition of both 0 and 1, and it gets collapsed when measured. So here's a little exercise for us to do together. Let's say that I have this qubit. Actually, this is a mathematical visual representation of a qubit. It's not a qubit in itself. It's called a Bloch sphere. But the little pink arrow is this vector is representing the state vector of this qubit right now. And it's pointing all the way up to a 0. So if this qubit is in this state, when it gets measured, we will read a classical 0. If it's pointing all the way down to the 1 state, when we measure it, we get 1. So now a question for all of you, with stretching our arms again, if you will. What happens when I measure this state? You don't have to all answer at the same time, but it would be kind of neat, in sync. You're going to say 1, 0. Can I see some arms up? No? No one wants to try to guess? Okay. So if you said 1, you're half correct. If you said 0, you're half correct. If you said 0 and 1, you're incorrect, and you're somehow inappropriate. So, mind you that I said, what happens if I make a measurement? If I measure just once, then it has to collapse to only one of the options, 0 or 1. So if I make several measurements, it will probably collapse half of the time to 0 and another half of the time to 1. And that's when the fun begins. Okay, so science fiction obviously will say that if you measure a superposition, the world catches on fire and you need the help of some superhero, but that's another story. And now I wanted to actually use this in a very practical way. And this is what I've been doing for several years now, also with the help of Chris at some point, creating a tool for musicians and artists to build, run, and simulate quantum circuits in a visual programming environment called Max, which Chris is an expert of and is one of the main responsibles for many of us to actually get into Max in the first place. And I built it a couple of years ago, and I called it the QAC Toolkit. QAC stands for Quantum Computing Aided Composition Toolkit. So let's see if I can do a live demo to show you this. So that is, by the way, a Max package. It's officially available on the Max Package Manager. If you search for the QAC Toolkit, it should appear here. So in Max, and for those of you who don't know, we just build everything visually with boxes and we connect them. So one of the objects that you can have access to once you have this package is OCH.microKiskit. The way we interact with it is by using messages. So let me create a message named quantum circuit to build a quantum circuit. I need to give it a name, and I'm going to choose QC. And I also need to say how many qubits and how many classical bits this quantum circuit has. I should have cleaned the console. So this here on the right side is the console that will let us know what's happening. So when I send this message, it confirms that it created a new circuit named QC. So now that I have this circuit, I can call it, mine is called QC, and add some gates. So by default, all qubits start at the 0 state, which is the relaxed energy state. So we can flip it, and I'm going to do here something really naughty. Oh, I made an error. So this is just to show that we start counting from 0, so the correct message should be QC x0 to add an x gate to the 0th qubit. Okay, now it had that. That's cool, but we now need to measure it, so we can also add some measurement gates, and we do it in a very similar manner. We want to measure qubit 0 on classical bit 0. Okay, so our quantum circuit is defined. It's a super simple quantum circuit. Now, in order to run it, we can send it to a real quantum hardware, or we can use a simulator. Fortunately, this toolkit includes a simulator entity, I call it, that we can create using a message called simulator. Similarly, we can give it a name, let's call it sim, and we can tell it what quantum circuit we want it to run. So it's named QC. All right, so we created our simulator. Now, to have our simulator do something, we can use its name, it's called sim, and get the counts. So basically, it's going to run this circuit multiple times, by default 1024 times. And because the only thing that I did was to change the states, flip the states, change from 0 to 1. For those 1024 shots, we have the result 1. Okay, but what if it was not in this simple state of either 0 or 1, but was in a superposition of those two states, an even superposition, more specifically? Okay, let's recreate this. I build a quantum circuit, add the gate, add the measurement gate, add the simulator, and request some counts. Now we can see that we have, for roughly half of the time, the 0 result, and the other half, the 1 result, which is what we were expecting. Okay, that's cool. That gives us an option between, we can choose between two things, right? That could be like major, minor, would you say? Yeah. But another question that we have, the recipe was to choose between 4 different notes of the diminished chord to be the root. So to do that, we probably need 2 qubits. So let's do that. And then maybe 2 Adamant gates. So we are adding an Adamant gate on both qubits. Let's also add the measurement gates on both qubits as well, and see what we got. We have different results for 0, 0, 0, 1, 1, 0, and 1, 1. That is like the simplest toy example and fastest that I could do in the time that Chris allowed me to speak. But I have just one more, which is I'm not going to patch by on the fly. I have it opened, I hope, which is how to go about choosing one between 1 out of 3 without having to discard one of these options. So there's different types of gates that we can use, and Hadamard puts the qubit in an even superposition, but we can use something like an RX gate that we can give it a parameter to put it in an uneven superposition. And that's what the next example is going to look like. Let me see if I can zoom in. Okay, so 1 out of 3, and this was actually inspired by a song by Breakbot. It's 1 out of 2. So here we have a quantum circuit with 2 qubits, and we are building it, adding an RX gate with a parameter to get an uneven superposition that would give us 2/3 of the time a 0 and 1/3 of the time a 1 on the first qubit, mind you. And then we have an anti-controlled Hadamard gate between 0 and 1. And then we have the measurement gates. So what this anti-controlled Hadamard gate does is that when the first qubit is 0, then it's going to put the second qubit in a superposition, which is great because we have 0 2/3 of the time, so we can split those 2/3 into 1/3 each, where the second qubit will change. So we will only have 0, 0, 0, 1, and 1, 0 results without having to discard anything. Okay, and I think I am back to the slides. Yeah, that's the recipe again, and off to you, Chris.
Okay. So we are running short on time, so I'll just show you a couple of passes of this program just to give you an idea of how different the results can be. I mean, they're the same and yet different. So this first one is an example where, as you can see, we start with the C major chord. We use this circuit to choose basically which of the 3 pitch class sets we'll choose as our diminished 7th chord, then which of those, which inversion it will be in, which determines what the bass note has to be. And then the other notes are chosen with a separate algorithm that does the voice leading just pretty much by choosing the most conjunct resolution. And then it does it again once it arrives. So in this case, it chooses chords that are more or less all interpretable as being within C major, so it never actually modulates, and it ends up on a first inversion A minor chord. And then in the second example, it ends up doing something rather different, which is it goes immediately to an A sharp diminished 7th chord in first inversion, and through various passes ends up ending up on an F sharp major chord. So I, of course, didn't do any of this harmonic analysis in making the example. I just simply ran the program, but I did the harmonic analysis retrospectively, and I said probably the simplest way to say it is that as soon as we get to that A sharp diminished seventh chord, we're on some sort of like secondary dominant leading to a B minor, which is part of an F sharp minor, and it ends up in F sharp major. Oh, do we not have an example of that?
Yeah.
Yes, we do. So obviously, F sharp major is a good ways away from A minor, right? So just very quickly, some of the things we think we'll try and do next is using other classically ambiguous chords. And in fact, it turns out that one of those very ambiguous chords in modern practice is the dominant seventh chord, which we think of as being maybe the most directional chord of all. It just says, I'm going to 1, or maybe I'm going to 6, right? But in fact, there are many, many places that in contemporary usage, the dominant seventh chord configuration might go. And so that's another exploration that we plan to do next. But also extending this into harmonies of 5+ pitches so that the landscape gets a little more complicated and a little bit more like the kind of music that I personally am interested in. And then assigning perhaps differing probabilities to all of these choices so that rather than making it a simple binary 50% likelihood or a 33% likelihood, we have continuously variable likelihoods, which would allow the music to be guided toward different either closely related or far related places. And I find that for me personally, this is interesting as a way to go beyond classical theory and go into places that, as I said, sort of create new harmonic orders, new harmonic grammars that are previously unheard but might still be very sensible and interesting. Do you want to do a plug for your thing?
Oh, there's still...
No, we'll pass those.
Yeah. Just to quickly add that we also have a website with resources for the paper. We know that both of us have to wear glasses, so if you want to look at the pictures more up close and the patch, you're free to go to this website. And also a little plug on this project. This project is from community.quantumland.art, a website database and a public online forum that I've created for everyone interested in creative practice in quantum computing. This is the first website, the Harmony, and this is the second one that has a forums on GitHub discussions where people are sharing events. MCM is there as well, as you can see. And there's, if I haven't lost the presentation, all that we have to say. Thank you.